For some reason, math teachers love the ladder problem for related rates. Here's the setup. You've got a 4-meter ladder leaning up against a wall, and starts to slide. The foot starts to slide to the right, and the top starts to slide downward. So each of them are moving with time. The problem tells us the top is sliding downward at 2 meters per second. So we're losing 2 meters per second with the height. And the question is, how fast will the foot be sliding when it reaches 3 meters away from the base? So it's at the moment when this distance reaches 3 meters. Here's our procedure for solving related rates problems like this. First, write down an equation relating the quantities in the problem. This is the hard part because depending on the problem, the equation could be anything. After we have an equation, then we should implicitly consider the variables as functions of t. So even though the height isn't explicitly listed as a function of t, we know that it's changing with respect to t as it's sliding down. So we'll consider that as a function of t time. All right, once we have this equation, we'll take the implicit derivative with respect to t on both sides. Then we go to the problem statement, find all the quantities we know and can figure out and plug them in, and then solve for whichever unknown is left. Let's work on setting up that equation. Okay, we need to pick some variable names. It's easier to talk about things if we have names for them. So let's call the height, let's call this y, because it looks like y-axis. And this distance from the foot of the wall to from the foot of the ladder to the wall, let's call that x. So we'll consider them implicitly as functions of time. Y equals y of t, x equals x of t. Off to the side for now. And we have a relationship between these quantities, x, y, and 4, given by the Pythagorean theorem. X squared plus y squared equals 4 squared, or x squared plus y squared equals 16. So here's our equation. So next we'll take the derivative with respect to t on both sides of this equation. Well, the derivative of a constant is 0. That hasn't changed. But since we're treating x and y as functions of t, we need chain rule to take these derivatives. So this derivative is equal to 2x, but then we're not done because x is a function of t. We have to do times the derivative of the inside function. So times dx dt. We'll make that a little neater. Times dx dt. Because we're imagining that x is a function of t, so this is by chain rule. And similarly, chain rule tells us we get 2 times y times the derivative of the inside part, which in this case is just y, so the derivative dy dt equals 0. Okay, so there's the calculus is done. Let's plug in what we can from the given information in the problem statement. All right, let's see what information we can plug into our equation from what's given in the problem. We were given that the ladder is falling at 2 meters per second. So that means dy dt equals -2. So it's falling at 2 meters per second. That means it's going down at 2 meters per second. All right, so then the height is changing at -2. So we've got 2x dx dt plus 2. Don't know why yet. We know this is -2. All right, it also asks, we want to find how fast this is moving when it reaches 3 meters away from the wall. So that tells us that 3 meters away from wall. This tells us that x equals 3. So now we've got 6 dx dt plus 2. Let's make that -4y equals 0. All right. Now dx dt, this is what we want to find. All right. And in order to solve for that, we need y. but we can use the Pythagorean theorem again to find y. Here's our triangle, 4, 3, and y. It's a right triangle. So y squared plus 3 squared equals 16. Y squared equals 16 minus 9, so 7. Y equals square root of 7. I'm not going to say y equals plus or minus the square root of 7 because these are distances, so they should be positive. So that means we have 6 dx dt minus 4 times the square root of 7 equals 0. All right, finally, solve this thing for dx dt. Just solve for it like a variable, and we'll get that dx dt equals 4 root 7 over 6 meters per second.